There's an experiment sitting in university labs all over the planet right now that Richard Feynman said holds the one true mystery of the universe. Not a big mystery, not a hard mystery. The mystery. He said if you could understand this one experiment, you'd understand everything strange about quantum mechanics. And if you think you understand it, that's proof you don't. So today we're going to break it apart piece by piece. And by the end, you're going to look at reality itself a little differently. Because this experiment suggests something insane. The universe doesn't fully decide what happens until something looks. Stick around, because the twist in the middle of this video is the part that made physicists question whether reality exists at all when nobody's watching. Let's get into it. In the early 1800s, a scientist named Thomas Young wanted to settle an argument. Is light made of particles, tiny little bullets, or is it a wave, like ripples on a pond? So he built something stupidly simple, a barrier with two thin slits cut into it, and behind it, a screen. He shined light through the two slits and watched what landed on the screen behind. Now, if light was made of bullets, particles, you'd expect two bright stripes on the screen, one behind each slit, because bullets travel in straight lines. That's common sense. That's how a wall with two holes in it works if you're throwing paintballs at it. But that's not what happened. Instead, Young saw a whole pattern of stripes, bright dark, spreading across the screen, like ripples from two stones dropped in a pond overlapping each other. That pattern is called an interference pattern, and it only happens with waves. Two water waves can crash into each other and cancel out in some places and pile up higher in others. That's exactly what light was doing. So the case was closed. Light is a wave. Book closed. Right. Except 100 years later, physicists doing completely different experiments discovered that light also behaves like it's made of individual particles called photons that hit a detector one at a time, like bullets. So which is it? Wave or particle? This is the open loop. Hold on to it, because the answer is about to break your brain a little. Here's where it gets interesting. Physicists eventually got equipment precise enough to fire electrons, actual particles of matter, one at a time, through that same two-slit setup, not light. Solid matter, sort of. One electron launched toward the barrier, then another, then another, then another, spaced out so there's no way they're bumping into each other or interfering with one another on the way. If electrons are just tiny particles, like tiny marbles, each one should go through one slit or the other, and after firing thousands of them, you should get two clean stripes on the back screen, two piles right under the two slits, just like paintballs on a wall. Instead, after enough electrons hit the screen one at a time, spaced minutes apart sometimes, an interference pattern showed up. The same wavy, stripy pattern you get from overlapping water waves. Let that sink wavy pattern you get from overlapping water waves. Let that sink in for a second. Each electron is a single, individual particle, arriving alone, with no other electrons anywhere near it. And yet over time they build up a pattern that can only happen if something is interfering with itself. It's like each electron is somehow going through both slits at once and interfering with its own path. A single object, splitting itself in two, overlapping with itself, and landing somewhere based on that overlap. That's not how objects behave in the world we can see and touch. That's the mystery Feynman was talking about. But it gets weirder, and this is the twist. Scientists thought, okay, if each electron is somehow passing through both slits, let's just watch it happen. Let's put a tiny detector right at the slits to see which one each electron actually goes through. Simple enough. Just observe it directly. So they did. They set up detectors at each slit to record which path every single electron took. And the moment they turned those detectors on, the interference pattern vanished, completely gone. Instead, the electrons started behaving exactly like normal particles again, landing in two clean stripes, right under the two slits, exactly like paintballs on a wall. The simple act of measuring which slit the electron passed through collapsed the weird wave behavior back into ordinary particle behavior. Turn the detectors off, interference pattern comes back. Turn them on, it disappears. Same electrons, same slits, same everything. The only difference is whether something recorded which path was taken. This is not a trick of the eye, and it's not about consciousness or magic, even though pop culture loves to frame it that way. It's about information. The instant the universe has a definite record of which path a particle took, that particle stops behaving like a spread out wave of possibilities and starts behaving like a single, located object. Before it's measured, it seems to exist as a kind of overlapping cloud of every path it could take. After it's measured, that cloud collapses down to one outcome. Physicists call this superposition, and the collapse of it is one of the strangest confirmed facts in all of science. Let's ground this with something from your actual life, because this isn't just lab trivia, it maps onto something real. Think about a coin spinning in the air. Right after you flip it, while it's spinning, it isn't really heads or tails yet in any meaningful sense. It's kind of both, a blur of possibility. The instant it lands and you look at it, that blur collapses into one definite outcome. Quantum superposition is a bit like that spinning coin, except way stranger, because the coin actually has a real orientation the whole time. It's just moving too fast for your eyes to track. An electron before measurement isn't secretly going through one slit while hiding it from you. As far as physics can tell, it genuinely has no single definite path until something forces that information to exist. That's the part that broke physicists' brains in the early 1900s. And honestly, it should break yours a little too. Take a second, pause if you need to, because we're about to go one level deeper. Here's where Feynman's real point comes in. He wasn't just fascinated that particles can act like waves. He was fascinated that this single experiment contains, in his words, the only mystery, because every weird quantum phenomenon you've ever heard about, entanglement, quantum computers, particles being in two places at once, all of it traces back to this same core idea. Reality, at its smallest scales, doesn't behave like a fixed, pre-written script. It behaves more like a set of probabilities that only becomes a concrete fact the moment it interacts with something else, whether that's a detector, a screen, or eventually your eye reading this sentence. Some of the greatest scientific minds who ever lived spent their careers arguing about what this actually means. Einstein hated it. He spent years trying to prove that particles secretly do have definite properties all along, that we just don't have the information yet, calling it hidden variables. He famously said, "God does not play dice with the universe." On the other side, physicists like Niels Bohr argue that there is no hidden information, that the particle genuinely doesn't have a definite state until measurement forces one, and multiple experiments since then have leaned hard in Bohr's direction. The universe, at least at this scale, really does seem to run on probability until something pins it down. Now here's the part most people never get told, the actual climax of this whole story. This isn't just true for electrons in a lab. The same double-slit behavior has been demonstrated with atoms, with molecules, and in 2019, with molecules made of over 2,000 atoms, objects almost big enough to see the shape of if you squint, and they still showed the same interference pattern, still behaved like spread-out waves of possibility until measured, which raises the uncomfortable question nobody has fully answered. Where exactly does this stop? Why does a molecule with 2,000 atoms behave like a wave, but you, made of trillions upon trillions of atoms, apparently don't? Is there truly a hard line between the quantum world and the world you live in? Or is it just that anything as big and as constantly bumped and measured by its environment as you are collapses into a fixed state so fast and so constantly that the waviness never has a chance to show up? Nobody knows for certain. That's not me being dramatic for views. That is a genuinely open question in modern physics, and it's part of why this 100-year-old experiment with 2 slits and a screen is still being run in labs today, because it's still teaching us things. So next time somebody tells you that reality is fixed, solid, and exactly what it looks like, remember that the most tested, most repeated experiment in the history of physics suggests otherwise at the smallest scales, and that the line between that strange quantum world and your everyday world is blurrier than almost anyone realizes. If this cracked your brain open a little, that's exactly the point. Drop a comment telling me what you think happens at that line between the quantum world and ours. I read every single one. Hit like if this made you see 2 slits and a screen completely differently. And subscribe if you want more of this, because we're going even deeper into what Feynman really believed reality is made of. I'll see you in the next one.